You know that feeling, right? You walk across the carpet, you reach for a doorknob, and bam, that tiny, surprising spark. It feels like nothing, just a minor annoyance. But that little shock, it's actually a window into an invisible force with some truly astonishing power. So let's get into it and uncover the science behind that spark. So, what's the connection between a t shirt that just won't stop clinging to you and a massive, catastrophic explosion? Believe it or not, the answer is the exact same phenomenon: static electricity. We're about to connect the dots from that everyday zap to some seriously world changing events, and it's all based on the simple movement of these invisible little particles. I mean, we've all been there. Your clothes are all tangled up coming out of the dryer. Your hair just defies gravity after you pull off a winter hat. Or, that classic party trick where you rub a balloon and stick it right to the wall. This isn't magic, folks. These are all just perfect, everyday examples of static electricity at play. To really get what's going on, we need to zoom in. I mean, way, way in. We're going down to the atomic level to see how this whole thing kicks off with a process I like to call the electron shuffle.
Okay, so literally everything is made of atoms, and at the center of an atom, you've got your positive protons. But the real stars of our show, the things that make all this happen, are the negative electrons, whizzing around on the outside. And why are they the stars? Because they're not stuck. They can move. They can jump ship.
And here's how they do it. There's this thing called the triboelectric effect, which is really just a fancy way of saying some materials have a higher electron hunger than others. They're just greedier. So when your wool sock rubs against the carpet, the material with the higher hunger literally steals electrons from the other one. It's really just a simple three-step dance. First, two things touch. Second, the transfer happens, the great electron robbery. And third, when they pull apart, the balance is totally broken. One object is now packed with extra electrons, making it negative, while the other one is missing electrons, leaving it positive. And that imbalance, that is static electricity. So what happens next? Well, this is where a basic rule of physics called Coulomb's law kicks in. It's super simple. Opposites attract, and things with the same charge push each other away. This is exactly why your hair stands on end. After you take off a hat, every single strand gets the same positive charge, so they all start pushing away from each other, trying to get as far apart as possible. All right, so we've got the basics down, but this is where the story takes a really sharp turn. Because that simple imbalance of electrons can scale up from being just a minor annoyance into a major, and I mean major, life-threatening hazard. Now, get ready for a mind-bending fact. That little zap you feel from a doorknob, that can be up to 20,000 volts. But the actual amount of energy, the current, is so tiny and lasts for such a short time that it just feels like a little prick. Okay, now compare that to the delicate little microchip in your phone or your computer. A spark of just 30 volts, so small you would never ever feel it, can send a killer surge through its circuits and completely destroy it. It's this wild paradox of scale. What's totally harmless to us is absolutely catastrophic for our technology. Just let that sink in for a second. 30 volts. The next time you're thinking about building a PC or even just opening up your laptop, remember that number. The danger is completely invisible, and you won't feel a thing, but it is very, very real and can turn that brand new graphics card into a very expensive paperweight. And it gets so much more serious. We're moving beyond fried electronics now. As this quote points out, in the wrong environment, think flammable gas or even fine dust in the air, that same tiny spark isn't just a nuisance. It's the ignition source for a massive, devastating explosion. And no, this isn't just theory. Look at these real-world incidents. Just in India, static electricity has been the root cause of some staggering disasters. Over 40 people died in a pharmaceutical plant because static ignited fine powder. 7 people died in a fireworks factory. A huge refinery fire started by a single spark from a tool that wasn't grounded. The point is, this invisible force has devastatingly visible consequences. And when you look into why these horrible things happened, it almost always boils down to a few key failures. Number 1, a lack of proper grounding, so the charge had nowhere to go. Number 2, dry air, which is the perfect environment for charge to build up. And number 3, simple human error, where a person's own body becomes a walking capacitor carrying the fatal spark. So, how do we fight back? How do we actually tame this invisible force? Well, the good news is the same science that explains the problem also gives us the solutions. We can absolutely build a defense against static, and it all starts with understanding how to control that charge. One of the biggest factors is just the air around us. Dry air is an insulator. That means it lets static charge build up to really high levels. It's exactly why you get shocked so much more in the winter.
But humid air? It has tiny water molecules that help conduct the charge away safely and naturally before it can build up. So the pros basically have a four-part playbook for this. The most important one is grounding or earthing. Then they control the humidity, trying to keep it between 40 and 60%. For stuff like plastic that you can't really ground, they use ionizers to neutralize the air. And finally, they use special anti-static materials that are designed to prevent sparks from ever forming in the first place. But let's really focus on the undisputed champion of static control, grounding. The concept is brilliantly simple. You create a direct physical connection to the Earth itself, which acts like a giant, endless sponge for electricity. Any extra charge flows right down that path and safely away into the ground, instead of building up and looking for a place to spark. It is, without a doubt, the single most important defense we have. Okay, we've gone through the science and we've definitely seen the stakes. So now let's make this really practical. Here's a simple checklist you can use to protect your gear and, way more importantly, to protect yourself. If you're working on a computer, the rules are simple and they are non-negotiable. An anti-static wrist strap is your absolute best friend. It keeps you and the PC at the same charge level. Don't have one? Then you need to get in the habit of constantly touching the bare, unpainted metal of the computer case. And please, for the love of all that is holy, never build a PC on a carpeted floor. And in those more hazardous situations, the stakes are obviously way higher. First, wear cotton. Synthetics like polyester are static-generating machines. If you're pouring fuel from one can to another, make sure the containers are physically touching. And here is the big one. When you're fueling your car, once you start, stay outside of the vehicle. Do not get back in. Sliding across that seat can charge your body up with thousands of volts, enough to create a spark when you touch the metal pump again. So we started this whole journey with a tiny, harmless shock, and we ended with catastrophic explosions and life-saving safety tips. It just goes to show how a seemingly minor scientific principle can have absolutely immense power. Which kind of leaves you with one last thing to think about. If a simple, invisible spark holds this much power, what other unseen forces are out there, shaping our world, hiding in plain sight?